Welcome to the presentation on derivatives. I think you're going to find that this is when math starts to become a lot more fun than it was just a few topics ago. Well, let's get started with what a derivative is. I know it sounds very complicated. Well, in general, if I have a straight line, let me see if I can draw a straight line properly. If I had a straight line, that's not a straight, that's my coordinate axes, which aren't straight. And let's see. Okay, so this is a straight line. When I have a straight line like that, and I ask you to find the slope, I think you already know how to do this. It's just the change in y divided by the change of x. If I wanted to find the slope, really, I mean, the slope is the same because it is a straight line. The slope is the same across the whole line. But if I wanted to, say, find the slope at any point in this line, what I would do is I would pick a point, x, right? So I'd pick this point. Let me pick a different color. I'd take this point, and I'd pick this point. I mean, it's pretty arbitrary. I could pick any 2 points. And I would figure out what the change in y is. This is the change in y. Delta y. That's just another way of saying change in y. And this is the change in x, right? Delta x. And we figured out that the slope is defined, really, as change in y. Change in y divided by change in x. Change in x, and another way of saying that is delta, that's that triangle, delta y divided by delta x. Very straightforward. Now what happens, though, if we're not dealing with a straight line? Let me see if I have space to draw that. Another coordinate axes. Still pretty messy, but I think you'll get the point. And let's say instead of just a regular line like this, this follows the standard y equals mx plus b. Let's just say I had the curve y equals x squared. Let me draw it in a different color. So y equals x squared looks something like this. It's a curve. You're probably pretty familiar with it by now. And what I'm going to ask you is, what is the slope of this curve? And think about that. What does it mean to take the slope of a curve now? Well, in this line, the slope was the same throughout the whole line. But if you look at this curve, doesn't the slope change, right? Here it's almost flat, and then it gets steeper, 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 until it gets pretty steep. And if you go really far out, it gets extremely steep. So you're probably saying, well, how do you figure out the slope of a curve whose slope keeps changing? Well, there is no slope for the entire curve. For a line, there is a slope for the entire line, right? Because the slope never changes. But what we could try to do is figure out what the slope is at a given point. And the slope at a given point would be the same as the slope of a tangent line. For example, let me pick say, green. The slope at this point, right here, would be the same as the slope of, make sure my pen, would be the same as the slope of this line, right? Because this line is tangent to it. So it just touches that curve, and at that exact point, they would have this blue curve, y equals x squared, would have the same slope as this green line. But if we go, say, to a point back here, even though this is a really badly drawn graph, the slope would be something like this, right? The tangent slope. The slope would be a negative slope, and here it's a positive slope. And if we took a point here, the slope would be even more positive, right? So how are we going to figure this out? How are we going to figure out what the slope is at any point along a curve like y equals x squared? Well, that's where the derivative comes in use. And now for the first time, you'll actually see why a limit is actually a useful concept. So let me try to redraw the curve. Okay, I'll draw my axes. Let's see. That's the y-axis. I'll just do it in the first quadrant. See, and this is, I really have to find a better tool to do my, this is x coordinate, and then let me draw my curve in yellow. So y equals x squared looks something like this. I'm really concentrating to draw this at least decently good. Okay, so let's say we want to find the slope at this point. And let's call this point A. right? At this point, x equals a. And of course, this is f of a, right? It's f of a. So what we could try to do is we could try to find the slope of a secant line, a line between. We take another point, say somewhat close to this point on the graph. Let's say here. And if we could figure out the slope of this line, it would be a bit of an approximation, right, of the slope of the curve exactly at this point. So let me draw that secant line. So let me, something like that. Secant line looks something like that. And let's say that this point right here is a plus h, right? Where this distance is just h. This is so a plus h. We're just going h away from a. And then this point right here is f of a plus h. My pen is malfunctioning. F of a plus h. So this would be an approximation for what the slope is at this point. And the closer that h gets, the closer this point gets to this point, the better our approximation is going to be, all the way to the point that if we actually get the slope where h equals 0, that would actually be the slope, the instantaneous slope at that point in the curve. But how can we figure out what the slope is at when h equals 0, right? Because let me see. So right now we're saying that the slope between these 2 points, it would be the change in y. So what's the change in y? It's so that this point right here is the x-coordinate is my thing is keep messing up. The x-coordinate is a plus h, and the y-coordinate is f of a plus h, right? F of a plus h. And this point right here, the coordinate is a and f of a, right? So if we just use the standard slope formula like before, we would say change in y over change in x. Well, what's the change in y? It's f of a plus h, right? This y coordinate minus this y coordinate minus f of a over the change in x. Well, that change in x is this x coordinate, a plus h, minus this x coordinate, minus a. And of course, this a and this a cancel out. So it's f of a plus h minus f of a all over h. This is just the slope of this secant line, right? And if we want to get the slope of the tangent line, we would just have to find what happens as h gets smaller and smaller and smaller. And I think you know where I'm going. Really, we just want to, if we want to find the slope of this tangent line, we just have to find the limit of this value, the limit of this value as h approaches 0. And then, as h approaches 0, this secant line is going to get closer and closer to the slope of the tangent line. And then we'll know the exact slope at that instantaneous point along the curve. And it actually turns out that this is the definition of the derivative. And the derivative is nothing more than the slope of a curve at an exact point. And this is super useful because for the first time, you know, everything we've talked about to this point is the slope of a line. But now we could take any continuous curve, or most continuous curves, and find the slope of that curve at an exact point. So now that I've given you the definition of what a derivative is, and maybe hopefully a little bit of intuition, in the next presentation I'm going to use this definition to actually apply it to some functions like x squared and others, and give you some more problems. I'll see you in the next presentation.